So okay, we have been discussing how to define a self-attention scores, also how to utilize this self-attention score to define the embedding vector for the inputs. We will mention how to use this attention score together with embedding vectors to define encode for a transformer. Right? Then in the next part, we can show you how to use the encoder to build a very deep transform model and how the architecture will be like inside the encoders and all the transformers. Before we have mentioned, given the input X, we can learn their corresponding embedding vector to be Z vectors, right? Actually, when we do the applications of this kind of mechanism in building the real-world transform model, the architecture will be much more complicated. So given the text symbols like these two words in one language, we can denote them as like x1 and x2, right? So according to the previous discussions, given this x1, x2 as the inputs, so we can utilize the self-attention mechanism for learn the embedding vector z1 and z2, right? Of course, we have multi-head self-attention, right? We can learn different copies of z1 and then further combine them together to define the z1 and z2 vectors. Actually, in the real-world application, when we apply them into building the transformer model or into building the encoder for transformers, we also have some mechanism inside it. So we incorporate the residual learning inside the model architecture. I hope you still remember when we learned the CM model, we mentioned resonate, right? And inside resonate, we try to create some higher ways to connect the inputs to the outputs, right? It will be very similar here. So given the inputs like x1 and x2, we learn the embedding vector z1 and z2 already. However, here we create one high way to connecting these inputs x to the output. So this is for the residual learning. We will have one copy of the input into the output. So before we mention how to calculate the z1, z2 with these two vectors by utilizing these attention scores and also mechanism based on the inputs, right? We have the z1, z2 already. Then furthermore, by utilizing this higher way, for the residual learning, we can add this a copy of the x1, x2 into the z1, z2 again to define new z1, z2 as shown here. Of course, we also have some normalization layers inside the architecture, to normalize the input result to be in some ranges. We have to normalize all the entries inside the result, then we can define new output to be z1 and z2 as shown here. And then remember, we also mentioned we have one feed-forward layer inside the encoder architecture, which will be feed this z1, z2 into one feed-forward layer. And here we also have this residual learning in this high way to have one copy into the result as output for the encoder. Then you can understand the learning process for the encoder inside the transformer. Given the inputs, we can learn the z1, z2 based on the attention mechanism. And furthermore, we have the high way for the residual learning. We have one copy of this x1, x2 into define or redefine z1, z2 as output, also subject to the normalization. And this one will be fed to the feed-forward layers and also do the residual learning with normalization layer again. Then we can generate the output. Here also we have a tricky part. Before we mentioned that the order doesn't matter actually. The word can be switched in any orders according to our requirements. However, in the real world applications, we also adding this x1, x2 with their positional encodings. What is positional encoding? Now, if this one is the first word, given the index of the word, so given the index of the word in a sentence, we can provide them with one unique encoding vectors for their positions. Now this one is the first one. We can encode this 1 into 1 vector. This is the second one. We can include this position index 2 into 1 vector as well. So by summing this embedding vector for the positions together with the x1, we can redefine x1 as shown here. This one will be used in the following part. So therefore, in applications for the transformer, we still utilize some of the information from the positions in the learning their representations. So this is about transformer and the encoder in the transformer. And in the real-world applications, we can have a very deep architecture for a transformer. We have multiple encoders, also decoders, right? In this page, we show you with the example how can we utilize kinds of encoders to build a transformer model with 2 encoders and 1 decoder as shown here. So given the inputs by utilizing 2 encoders, we can compress the input into some concise embedding vectors, right? Which will be serving as the input for decoder for generating the result. This is the tricky part here. For the decoder, besides the embedding vector from input from the encoders, we also have some extra inputs as shown here, right? These are the extra inputs we feed to the decoder. You may wonder what they are. For these extra inputs for the decoder. This one will be optional depending on if we have it or not. If we have the actual input, we can also feed them to this decoder. If we don't have it, then we can assign them with some time value instead. It will not affect the performance for the model actually if we don't have these inputs. And then furthermore, we can generate some outputs based on the decoder result, and we can get some results as output and as a final output, as shown here, right? Okay, this is the architecture for the transformer with encoders, with decoders. Inside it, we have attention mechanism, we have this residual learning, we have the normalization, and so forth, right? So by going over the previous pages for the slide, you can, should be able to understand what we are doing inside the transformer model and what we are doing for the self-attention mechanism. And then in this page, we plan to show you how to use this transformer for translation one language into another. So in this system, we have a sentence input from one language, like this one. And we can represent the input text as some vector like x1, right? At the same time, according to the word position inside the sentence, like we can provide the positional embedding as well, like this one, right? This is the first word, we can provide the first word embedding vector for the position, and the second one and the third one, right? So by combining this embedding vector for the word together with the position, we can feed them to the encoder, right? For translating sentence into another language. And we can illustrate the translation process because this one is a sentence input, and we have to generate the output word by word as a result, right? So we can illustrate the translation process by feeding this one as the input to the encoder. We have the embedding vectors, right, which will be like these vectors. And we can further feed them as the input for the decoder. Then we can further generate the output. Now the first word will be I for the translation, right? And so this is for the translation of the first word. And in a similar way, we can also do the translation for the remaining word as well. Because right now we are saying we have generated the I as the output already. When we translate the second word, we'll feed this I as the input for the decoder as well. So when we translate the second word, for the result, besides the input from this sentence, this input sentence, we'll feed in this prediction from the previous step at the input for the decoder as well. Then in this way, we can generate, for the translation, then we can generate the second word as output for this sentence, like I am. And so forth, we can also feed this I am as input for the decoder again when we translate, for the third word as output, and so forth, right? So you can see that's the reason why for the decoder we also have some extra inputs, which are the translation result from the previous steps. We will be feeding them as the input for the following steps, as shown here. And this process will stop until we can reach the end of the sentence. If we find that the prediction result for the current step is a stop token, then we will stop this process and we can generate the complete translation result for the sentence input. Now this one, the translation result will be I am a student, as shown here, right? And we stop this translation, reaching the end of the sentence, as shown here, right? Okay, so this is the transformer, and how can we utilize the transformer for translation of one language to another language. In this page, we'll show you the different kinds of versions of a transformer model used in academia or the industry, also the number of parameters incorporated inside them. So the x-axis denoting the year, and starting from 2018, generally people have been keeping working on this transformer and their variety models all the time, right? So we have different versions of transform proposed already, like GPT or the switch, as seen by here, right? So most of them, they have very nice model size. For example, for the GPT-3, the model size, the number of parameters inside it is more than 175 billion. And this one, the switch C is much larger. It is 1.6 trillion of parameters. So the transformer model right now is very powerful. At the same time, it's also very huge. It's very big. If we plan to train one single model on GPT-3, it takes several millions of dollars to train, also a long time to train the model. The training process is very slow, also consume not so power, not so resources, not so money, and lots of data actually. So the transformer model nowadays is very powerful. Also it is used almost everywhere in academia. And we can show you with one example. It's called BERT, and which can utilize the transformer as an encoder for compressing input into some embedding vectors. Also, we can combine the transformer with some pre-training techniques for the model transfer as well.